John earned his PhD in nuclear engineering from Penn State in 1997. I actually knew him at that time, or even before that time a little bit. And then he went to work for Holtec International for a few years as a principal engineer. From there, he switched to Oak Ridge in 1999, and he rose up the ranks rather rapidly, leading there as a division director to join INL initially as chief scientist of the MFC. This was in 2016, and again he rose up the ranks very quickly, and now he is where he is as a social care director. John has many accolades to his name. I'm not going to go through the full list so that he gets a chance to speak a little bit too. But he is an ANS fellow, and he is a winner of the EO Lawrence Award, one of the highest, I think it's the highest or second highest award that's given by the Department of Energy.
Yeah, there's still the Fermi Award.
Yeah. That's very good company.
I'm not gunning for that one. I don't think I'm not going to get that one.
So with this, I would like to ask you to join me in welcoming John.
Okay. All right. Thanks, Yusri. Appreciate that, and appreciate the invitation to come. It's always a pleasure to get out here. It's been a little while, and appreciate the turnout as well. So thank you. Hopefully it'll be worth your time. I've got fairly high-level slides. So what I'd like to do is anytime that you want to ask a question or dive deep into something, I'll dive as deep as I can. Feel free to. I love to have discussions as opposed to a one-way. But we'll see if you all want to do it that way or not. Before I get started, maybe to help me, so how many people think they know reasonably well what INL does and who, and about INL? Okay, so quite a few don't. Okay, how many have actually visited INL? And I know you. Okay, all right, so just give some context. Okay, thanks, that helps me. Then sorry to make this awkward, but I'm always kind of curious what the audience thinks. And then how many people are like super optimistic about nuclear energy? I mean, it's a nuclear engineering department. I would figure I get pretty good. Okay, kind of, that's most of you. It's kind of some bashful kind of ups there. How many are pessimistic? Okay. 1, 2, 3, 4, 5-ish, 6-ish, maybe. Okay, good. All right, good. So tell me, the pessimistic group. Maybe we can powwow afterwards and see if I've influenced you at all in a positive or a negative way. Because let me just get right into it. So you know who I am and all that. So let's move on. This is high-level stuff. I'll try to go over it pretty quickly, but I like to ground things on why am I optimistic about nuclear energy? Why am I committed to nuclear energy? There's more reasons than this, but fundamentally, all their studies out there are predicting that temperatures are rising. Is it because of carbon emission? Is it because of human activities? I'm not certain. I'm not a climate scientist. But there are an awful lot of smart people that are correlating those things. And even if you're not a believer in that sort of thing, when you look at verified studies of how many people die early every year around the globe because of air quality and air quality related issues, it's phenomenal, okay? And so just in terms of temperature and air quality, there are better ways to be generating electricity than what we're doing now, and we know how to do that. Another important piece is energy growth. We kind of have the luxury in this country that our energy growth has not been substantial over the last couple of decades for a variety of reasons. That's not the case around the globe. Predictions are, and they can put a plus or minus, it's still almost 30% energy growth between that. That's only 20 years away. That's substantial. Where is that energy going to come from? Is it going to come from clean sources or not? Is it going to come from nuclear or coal or what have you? And a lot of this obviously is not in the U.S. The big wild card for U.S. energy consumption and demand is whether or not we continue at a rapid pace to electrify transportation and things like that, or not. And if we do that, we'll see a significant increase in electricity, obviously, in demand in this country. And if we don't, we will probably stay fairly slow, fairly stable to mildly increasing. So this is important for the planet, all right? And again, even if you all are skeptical, I mean, I'm used to talking to people who are pretty skeptical of climate change. The world is not, okay? So in some ways, it doesn't matter what you think, because the world is already speaking and they're taking actions. And there is a global market for clean energy and nuclear energy that somebody is going to fill. Russia, China, US, that remains to be seen. So this is a big deal. What you all are studying, what I've committed my life to, in my mind at least, is a big deal. So I'm going to get into some context about 3 priorities. Generally, I bucket things in the current fleet, what comes next, advanced reactors, and fuel cycle and spent fuel. These are the way I kind of bend my thinking about what we're doing. If you look at the current fleet and you watch the news and you read, I'm assuming you all do, it doesn't look very positive most of the time. We've got a number of plants closing for, I probably don't need to tell all you this, but there's a lot of news out there. I'll just say that I'm not going to read these bullets. There's a lot of news out there that looks pretty pessimistic. And the flip side of that is, in the meanwhile, these things keep operating safely. They keep generating the vast majority of our carbon-free energy. They keep increasing the power output from nuclear energy without even building any new nuclear plants coming online. It's actually an incredible record of performance that these plants do, even though they're under these economic challenges. Now, we will lose more of these plants. You know, there's various studies out there that would suggest there's a good chance we'll lose another 25 to 30 of them over the next 5 to 10 years. But at the same time, that's also served as a major wake-up call. And you're seeing quite a number of states, I think I've listed them here somewhere, that are taking action to preserve these plants. Because while while utilities are considering shutting these plants down, states and utilities are setting clean energy goals. Some of them 100% clean by 2040, and they really have no idea how they're going to get there. And so you're seeing some of these actions coming in to fix that. So there is a lot of pessimistic news, but I would tell you the momentum is in the right direction. The momentum won't save them all, especially the older single unit plants. It's just the reality. In the advanced reactor space, I'm probably going to spend more of my time talking about advanced reactors and advanced reactor deployment than any other topic, because this is really what's changed. I've been in this field for quite a long time now. I've never seen anything even remotely like the opportunities we have in front of us today. Nothing even close. I mean, it reminds me, it must have been back in the 40s and 50s when we were demonstrating reactors and these things were new again. We've never had this kind of bipartisan support. We've never had this kind of budget. So to put it in perspective, if you looked at the Office of Nuclear Energy's budget 6 years ago, it was around $700 million. The current fiscal year budget is $1.5 billion. And the story is not just about the Office of Nuclear Energy. When you look at NASA re-engaging at over $100 million a year and in fission power for nuclear thermal propulsion, you look at the Department of Defense's budget for their mobile microreactor at $70 million, and all the other things that are going around that. It's I've ever seen before. And then you look at these legislations. So I'm used to 5 years ago, various senators and congressmen introducing nuclear favorable legislation. We'd get excited, this is good. And they never passed. They never passed either. They didn't pass out of conference, or if they passed out of conference, they just died. Now we're seeing things like NECA. I hope you all have heard of the Nuclear Energy Innovation Capability Act. It authorized the Versatile Test Reactor. It authorized the National Reactor Innovation Center, among other things. NEMA, which authorized some reforms in licensing. That's the Nuclear Energy Innovation and Modernization Act. And those both were signed into law. And then NELA, which has a whole bunch of stuff I won't go into, but there's really great stuff in the Nuclear Energy Leadership Act. as well. I'm not as optimistic about that one passing and being signed into law. But in some ways, it doesn't even matter because the effects of what's in the NELA legislation has already trickled into appropriations language and actions. Things like NELA calls for 2 reactor demonstrations by 2025. The current budget appropriation language, $1 million for 2 reactor demonstrations to be done in the next 5 to 7 years. So you're seeing these kinds of things flow. And if you look at it as a snapshot, I won't read this to you. You probably can't read it either. But if you look at it on a 1 year perspective, there's a lot of positive things. If you look at it on like a 5-year perspective and watch the budget growth, watch these different things, and that's basically what ClearPath has done, checking off all the things that are happening. It's really quite an amazing story that's going on right now. And so for those of you who aren't optimistic, I don't know how you can not be optimistic about this, but we'll talk maybe after I'm all done. This is an area you could be not optimistic about. So spent fuel. So I spent a good portion of my career working spent fuel issues, storage, transportation, actually Yucca Mountain too. Yes, I was involved in that. It's pretty disappointing when you do all that work, and it does, and we are where we are. But I'm still going to put a bit of a positive spin on this. Despite the fact that we don't have a national repository, which we absolutely must have, we've continued to store spent fuel, move it around when we need to, safely, securely, without incident, even though it's very suboptimal to have this material all over the place. And it's a significant challenge when I talk to probably you and general public about I want to build a bunch of advanced reactors and I don't have a final resolution for the spent fuel. There are some that would say the final resolution is we store it until it's a valuable commodity and we use it. That doesn't feel, I mean, I'm not against that, but it doesn't feel that satisfying. It's not kind of that final closure that we're looking for. But I could talk a lot about this if anybody wants to, but for now I'm going to move along. I'm going to give you a brief, just real brief, of the Idaho National Laboratory for context. And the main point I like to talk about with this slide is, we've been called a bunch of different stuff. Now we're called the Idaho National Laboratory. But for me and for all of us, in the last few years, we've been thinking a lot about our origin. What is now the Idaho National Laboratory was established in 1949 as the National Reactor Testing Station. So during this period of time, from 49 really to kind of in this time frame, 52 different reactors were demonstrated on the site by a variety of different organizations. And really an amazing time. And the first electricity generated, the first town powered, the first mobile Army microreactor that was demonstrated mobile. I mean, there's all these firsts that happened in that period of time. Then we got into 94, we shut down EBR2, we shut down TREAT, and moved from an energy mission to an environmental cleanup mission. These are what I call the dark days, and I'm glad I was not there. And kudos to the folks that supported that important mission. In 2005, the laboratory was formed really out of a combination of INEEL and Argonne. So you took 2 organizations and you put them together. There's lots of stories about how that went. But and we've heard of this period as building a laboratory because it really wasn't a national laboratory at that point. It was really a cleanup site and a part of a national laboratory put together. And I'm really excited that I almost didn't live through most of that too. And I'm coming in at this awesome time when we're gonna build reactors. So really going back, preparing over these years to what we were doing back then. Of course, we're going to do it differently, but we're gonna do that again. Give you a sense. This, when I went out there, I spent about 17 years at Oak Ridge National Laboratory, an Office of Science laboratory. INL is the Office of Nuclear Energy's laboratory. So they have different missions. But the one thing that was just kind of blew me away is how big this site is. So it's 890 square miles. There's reasons it was selected as the National Reactor Testing Station. There's reasons that significant testing with ballistic missiles and tank armor and things like that were done on this site. There's a lot of land out there that enable you to do things at scale that you can't just do anywhere. We have our own grid, we've got multiple reactors, we've got our own, I mean, just all this stuff. I mean, basically it's like its own little state. You know, it's not that much smaller than the state of Rhode Island. It gets confusing to people because of that. So we said, did I visit INL and I went out to the site? People call this the site. What does that mean? There's a whole bunch of sites. So I started my career at at INL, at the Materials and Fuels Complex. And that doesn't look like very far, but that's almost 40 minutes away from the in-town office where I work today. And then you go out further and there's Advanced Test Reactor. And then you've got some various other things like the Critical Infrastructure Test Range Complex. You've got special manufacturing capability way up there to the north where they make tank armor and other things. So there's just a whole lot there. Currently we have 4 operating reactors. We've got the Advanced Test Reactor, the TREAT, which is a transient test reactor, a small trigger called NRAD that we use for neutron radiography, and then the ATRC, which is a critical facility to support ATR. We have spent fuel, I mean, there's just a lot of stuff there. This is not actually, this needs to be updated. We're about 5,000 employees now and about a $1.5 billion budget now, so there's been a lot of growth. This is how we're organized. Nuclear science and technology is what I lead. I work very closely with Sean O'Kelly, who runs the Advanced Test Reactor. Obviously, we do a lot of irradiation. And the Materials and Fuels Complex, if you haven't ever been there, it's really an amazing place to visit. That's where all the hot cells are. So Materials and Fuels Complex has the kind of entire suite that you need for materials and fuels testing. The basic ingredients are there, whether you want plutonium, americium, neptunium, uranium, whatever, they've got it. There's obviously a bunch of, there's no pictures, but there's a bunch of guards and things like that. They can make fuel in small quantities. We can characterize it. We can ship it over to ATR or TREAT or wherever you want to radiate it, bring it back into the hot cells, do post-examination irradiation, make it smaller, do various microscopy. We've really advanced the number of instruments we have for that over the years. And then there's also the TREAT reactors associated here as well. So there's just a tremendous amount of capability there. We do a lot of work at the laboratory that's not nuclear. I kind of refer to Todd Combs' organization as energy, everything except for nuclear. And we work very closely with them on some things, and I'll refer to that later. And then National and Homeland Security, that's kind of a mix of nuclear nonproliferation and physical and cybersecurity. These folks are most known for, and the biggest part of what they do is control system cyber. So my organization, to help you understand what kind of capabilities are in it, it's reactors, it's regulatory research, which includes things like PRA and risk analysis, so forth. Computing, we just moved into a new computing building called the C3 building, which is a mix of the high-performance computers that we have. Now, these are not the high-performance computers you might think about like exascale. These are petaflop computers. Our newest, greatest computer is only 6 petaflops. What we need, but not bleeding-edge kind of computing. That's also where the things like AI research and Moose and those kind of code developments exist. Fuel cycle science and technology, so that's things like aqueous processing research, pyro processing research. They have a lot of experience in that area with molten salt, so we're doing more and more molten salt reactor type work because of that experience. And then spent fuel storage and transportation, and very, very limited amount of disposal related work. And then the last but not least is nuclear fuels and materials. That's actually by far our biggest division. It's really our specialty, largely because of the capabilities at Materials Fuels Complex, Advanced Test Reactor, and so forth. But that's everything from designing experiments to simulating those and their performance to executing the entire kind of process around that, to actually designing new materials. A lot of the TRISO fuel development work, for example, is done in that division. We lead a number of NE programs. The Office of Nuclear Energy, which I'll call NE, is our biggest sponsor. And we lead a number of their programs. Hopefully you've heard of the Gateway for Accelerated Innovation in Nuclear. NSUF, if you wanted access to some of the facilities to do some materials research, for example, you write an NSUF proposal and you gain access, and even the people that perform those experiments, you gain that whole resource through that opportunity. Advanced reactor technologies, there's 3 different campaigns, and they're technology related. Molten salt reactor campaign, there's a high temperature gas reactors, and then there's the fast reactor campaign. There's another one, there's the micro reactor R&D program as well. Light water reactor sustainability, again, focused on the sustainment of the light water reactors. Probably many of you are familiar with that. And I probably shouldn't go through all of them, but well, these modeling and simulation ones are probably pretty interesting to many of you. There's been the CASTLE program focused on light water reactor simulation. NEAMS, the Nuclear Energy Advanced Modeling and Simulation, has been focused kind of on everything else. CASTLE finished its 10 years at the end of this past fiscal year. I mean, they're still continuing, but they're wrapping up. And there's now a combined program that's been conceived and is starting to execute. So NS&T, I know these are, again, high level, but we really, our vision is to change the world's energy future through advanced nuclear. Our mission is enable nuclear energy expansion, not just sustainment, expansion through innovation. This is it's capitalized for a reason. I know you all are young and most of you are new to the nuclear field, but I'm not. And the nuclear field has been pretty evolutionary, pretty risk averse in research, even in research decisions and research programs. Oftentimes we set goals that we absolutely know we can meet. We set milestones we know we can meet. And that's just not gonna cut it, all right? So we have to be way more risk tolerant in our research programs. We've got to innovate much more than we've done as a community. That's my opinion. I mean, it's an opinion. It's something I think we absolutely have to do. So one of the things we're doing at the laboratory is really trying to push acceptance of risk and even failure in our research programs, and strive for things that we don't know how we're going to get there. Set targets that we don't know how we're going to achieve them, but to drive towards achieving them. I already talked about our priorities: existing fleet, expansion, and spent fuel. So let me get into one slide on each of the 3 areas to give you some, and also to help feed what is the research, what are we actually doing. I can't go, I won't go too deep unless you ask questions, and then I'll go, like I said, as deep as you like. But the bottom line for the existing fleet is most of them are not economically viable. Okay, not all of them, but a number of them are struggling to compete in the current marketplace and in the way that the electricity markets are priced and so on. And so we've got to reduce their operating costs and or increase their revenue. All right, so that's really the high-level focus of any of these research programs. All right, if you're not doing one of those 2 things, what are you doing? Well, there is one more thing, and that's been traditionally these kinds of programs have focused on life extension. Okay, so subsequent license renewal and then subsequent license renewal. So if I was here in front of you 5 or 6 years ago, the slide would look quite a bit different, and it would be all about the markets were not such that the issue was, can we get a license extension? Materials research, aging and degradation type research. And that has changed. A lot of good research was done. The technical basis is there. The NRC has openly said we don't see any showstoppers, generally speaking, to going to 80 years. 80-year applications actually have already been approved, and there's several in the hopper. So that's why it's shifted the focus to economics. So we're doing a lot of research. We're just doing a little bit in this space, valuation of the attributes that nuclear does and how nuclear fits in an integrated energy systems to inform policy. We don't do a lot of work in this space. We probably should be doing more work in this space, but that's why I'm going to keep it here until I can come here and think we're doing the right amount of work in this space. Then these are some examples of things that affect the sustainability and the cost of these plants. And they're just examples. In this, we are looking at, and this is where CASTLE contributed as well, looking at better simulations for the plants to try to recapture safety margins. In some cases, that can enable you to reclassify the safety significance of components, which then affects a lot of downstream things like how frequently it has to be inspected, who it has to be purchased from. You guys have probably heard the stories about what a nuclear grade bolt costs versus a regular grade bolt as an example. There's things that have been in place for a long time at the NRC, processes like 5069 that haven't really been all that executed. Utilities like Exelon now are executing those processes, reclassifying the safety significance of components and saving themselves a lot of money. Switching over to this, there's a lot in here in terms of modernization and sustainment. But what I'm going to talk about just under this one is I'm just going to be blunt, we've got too many people operating these plants. Many of these plants were started up with 200, 250 people, okay? Now, that was a long time ago. Many of these plants now are operating with 600 to 700 people, okay? That's what's happened. You can trace it, what happened. 3 Mile Island resulted in INPO and a variety of things that increased staffing. 9/11 increased a lot of security. And so there was kind of trending, but then you can see some big step functions in staffing. And so that's a big part of the cost is people. And so you got to think about how can we do these jobs more automated? How can we do these jobs more efficiently? And there's a number of things that plants are already doing. Because of the pressures on the costs, they have already started to be more innovative than they were for the last 20 years because they really didn't have to be. They were just kind of cruising along, making electricity and at a good price. So the simple thing, the way I'll put it here is as an example, is sensors, all right? So if you have an old car, you change your oil every 3,000 miles or 5,000, whatever you choose. If you have a new car, it tells you when to change the oil. Well, we're actually just implementing a lot of sensors and things so you have health-based maintenance, health-based inspection, automated inspection, things like that to help reduce cost. There's a whole lot more in here in terms of control room modernization, digital controls. There's actually a lot more than what I'm saying here. Accident tolerant fuel, yes?
You said there was an increase in staffing, correct? An example is that after 9/11, you started to see an increase in security. Do you also see increase in staffing inside control room? What kind of scenarios would you have?
Do not see a significant increase in staffing inside the control rooms.
So it's all outside, external staffing?
Internal to the plant, but external to the control room, yeah. So, I mean, I probably pretty much said it. There's a variety of safety things, when you say, okay, I've got a safety concern or a corrective action or whatever, you bring people in, and sometimes those people then stay. It keeps kind of building on itself. I'm not actually even saying anything was wrong. After 9/11, there's a lot of important safety improvements and practices and cultural changes that went into place that are really important. I'd say we went too far. All right. So when you talk to utilities and they have literally thousands of corrective actions every year, and you ask them what the value added of those corrective actions are, you get a funny look. There's just a lot of things I think that have been taken too far. On accident tolerant fuel, I'll mention it started, well, at least most people kind of first got aware of it related to post-Fukushima, looking at, for example, claddings and fuels that could survive longer during such situations. And that's still the principal focus. But the utilities don't necessarily need greater safety. All right, their fuels are already safe enough. They're approved. So the question where they get really interested, and if it's going to cost more, why would they change? But they get interested in, is there features coming out of this fuel that could allow me to save money somewhere in the system? Could it allow me to reclassify certain safety components because I have a longer period of time before I've got to take an action? Could it allow me to actually completely make some systems not safety significant? And that all has to work itself out. The trend, by the way, here now is maybe that doesn't get them as much as they want. And so there's kind of a renewed interest in much higher burnups, and higher enrichments, in like, let's say up to the 7% range. So that's really what a number of utilities and EPRI and others are pushing for. Now, you take that, you combine it with some of the accident tolerant aspects of some of the fuels and claddings that are being developed, and they see some real potential for economic improvement in that. And so there's an awful lot of work going on in this realm. So quickly, I'll just move to this middle one. This is the one that all the other ones I was talking about, I would say, are more focused on reducing the operating costs. This is where we have the potential to improve the revenue side of the equation. So there are a number of plants that at certain times of the day, certain seasons, they have to compete with significant loads of wind or solar, and to where the price of electricity goes very low, and in certain markets, particularly in the Midwest, it actually goes negative, which means they pay the grid operators to take their electricity. And so, I mean, you know, who wants to make a product that you pay somebody to take away? And so what they're looking for is obviously a different business model under that circumstance. And it's been really interesting for me to watch this field. We call it integrated energy systems. I'll move it over here. Today our focus is we simply make electricity with the plants. But what happens when you're not making significant money or even having to pay? What could you do with that electricity? And what could you do to make revenue from it? So a number of the utilities have got, and this used to be kind of something, well, maybe someday advanced reactors will make hydrogen and so on. So it was kind of, up until recently, maybe a longer term kind of thinking. Well, now the utilities are going, now I can bring in an electrolyzer and make hydrogen. So I can just redirect my electricity with no changes to my plant and make hydrogen when the price goes to a certain price point where it doesn't make sense. And so there's been a lot of market analysis studies done to see when this might be the right thing to do. And that's all great. But why I'm excited about this area right now is there are several utilities who are now buying equipment to demonstrate it. So we've got a collaboration with First Energy, Ohio, upper Midwest, Excel, also up in the northern Midwest region where they have a lot of wind. And then Arizona Power or Arizona Public Services to actually hook up electrolyzers, make hydrogen. They've got a plans to where they're going to sell the hydrogen to, and just get some experience with this process. Exelon has also, we also have a project with Exelon to do a very similar thing. And so this is really important because at some point we want to see these nuclear working well with other intermittent sources, and how is that going to work in an effective way? And so that all fits into that. Does that make sense? Okay. So switching to advanced reactors, I don't think I need to give you guys a tutorial on reactors, so I'm going to hit through these slides kind of quickly. The big thing that I want you to walk out of here with in this space is that we're not talking just about your grandfather's reactor anymore. All right, there are different needs beyond the big gigawatt scale reactors. And so, yeah, my animation's messed up, so it's okay. But this is just a slide on big reactors. This is what we're all used to. This is what the world's used to. If you ask somebody off the street what a nuclear reactor looks like, if they know it all, they would say big cooling towers, giant facility, many acres, big thing, a giant footprint. And it looked like this. This is incredible. If you guys don't go to the Vogel website and watch their they take photos, on a regular basis and show the progress. It's incredible. This was, maybe still is, the largest construction project in the country. Last numbers I saw were $28 billion to complete. And you all probably agonizingly see the duration that this has gone through. There are certain parts of the country and there are certain parts of the world where this is the right answer. You need that much power. Now, the right answer, maybe not that price point or that duration, but you need that size of reactor because you simply have that kind of need. China, I think they're going to have a half a dozen additional reactors come online. I think it's within the next year. And so there are places where energy demand is just growing at that pace that makes sense. And so we do have to do research, by the way, to make this more cost effective and timely. But in the US, honestly, after this is done, and maybe somebody will buy the reactors in South Carolina and finish them, I don't see a lot of this happening in the US I might even say my lifetime. So because of all the challenges with the big reactors, you saw the small modular reactors emerge as a possibility. An option where you don't need a gigawatt, you need something smaller, maybe that's a few hundred megawatts. You don't need it all at one time. You can modular, you can add it in as you need instead of committing to the whole thing. And you don't have everything stick built. You have a number of things that are manufactured in factories, brought in and installed. In the case of this concept, this is NuScale's. The idea is that the entire reactor module is built in a factory, shipped there, and simply installed. You still have a pretty significant construction project for the overall, buildings and so forth. But to the extent possible, you take advantage of modular construction and factory construction to reduce costs. You have that modular standpoint. In this particular design, to use as an example, this is a 12-pack. So you can do as little as 60 megawatts, and you can fill the whole thing out and have 720 megawatts as you need it, ideally. Another neat thing about this is you could refuel one at a time, and so you're always generating electricity as opposed to going from a gigawatt to zero. So trying to improve, cost effectiveness and flexibility. And my opinions on this is there are markets, even in the US, for that amount of power. Still got to get the price point right, but the markets are there. And certainly there's a lot of interest overseas for this kind of power. So I do see these reactors being built, and I'll come back to that a little bit. But kind of taking it to the next level is microreactors. So those of you who've talked to me, I'm really big on microreactors, no surprise to you. And why is that? Because it started with a market. So I didn't see a strong market for the big reactors in this country. I keep in mind most of my comments, and looking globally is very different. Even SMRs, price point and that much, there's not a ton of demand there, and I'll talk about that a little bit more in a minute. But microreactors were something where there is a absolute need. The first need I became aware of was remote communities in Alaska and Canada, where you're competing with diesel generators and diesel fuel that is shipped in, and sometimes ice roads and sometimes barge. Sometimes they fly diesel fuel in, depending on what it is, and burn diesel fuel. So you can imagine the cost of the diesel fuel isn't even the big issue. It's the transport of the fuel there. So the price point is way different. So it's always nice to compete in an area where the price point is terrible, or really good in this perspective. So we know we could compete in that space. All right, and by the way, you're competing with anywhere from 30 cents to $2 a kilowatt hour, depending on kind of how remote they are and what that situation is. So if you can't build a small nuclear system that can compete with that, we're probably out of business at that point, I think. So, but we believe we can. In fact, I'm quite confident we can, and so are others. And so there's people investing even private sector money into this. But what got really interesting for me was, okay, that's a market. Maybe that's a couple hundred units. Maybe it's 500 units. All right, and that seems great. It's a market. That's good. But over time, as we've talked to other people, remote mining, think about oil and gas exploration and extraction. Think about anywhere where you have to have absolute confidence that you're going to have continual, reliable power. And then you think about anywhere there's a diesel generator is a potential market for a small reactor. Now, again, the price point has to be right, and the operational aspects in terms of is it difficult to operate, and so forth, have to be right. And that's ultimately what will constrain these microreactors from either a deployment of 5 or 10 to a deployment of 5 or 10,000. And everywhere I go, I see new applications for these. And I'll give you another one that surprised me, cargo shipping. Cargo shipping is done with diesel, all right? Some of those really big systems, they claim, I didn't verify this, that they burn 80 tons of diesel fuel a day, all right? So you think about that, and you think about the environmental regulations internationally that are now being implemented that would require them to stop doing that in the 2040s. What are they going to do? what are they going to do for a power source? Maybe it's nuclear, maybe it's something else, but maybe it's nuclear. So a lot of really different applications. I've probably touched on a number of them there. I did not touch on the disaster relief aspect. There's Puerto Rico actually has gotten really interested in small nuclear systems for reasons I think you can imagine. To be economical, these things are going to have to not be your traditional massive emergency planning zone region, not have a control room and so forth, not have. If they have all that, they probably won't be very economical, and the ultimate, again, market share will probably be pretty small. Any questions so far on that?
Yeah, why is that? Why you don't require a security zone and things like that?
So what I said is, if they're going to be economical, you need to not have a big emergency planning zone. And so we have to be able to demonstrate that that's possible. So there's a number of things that we have to go through the process to demonstrate that that's possible. We are seeing some great movement by the NRC on emergency planning zone. For those of you who follow this area, TVA early site permit went from a traditional 10-mile radius emergency planning zone to 2. So we are seeing some nice movement in the regulatory for methodologies that permit you to start shrinking these down. A number of the microreactor developers are trying, I can't speak for them, but they're working towards a technical basis for an emergency planning zone that is as big as their site or even as small as their building. And so, of course, you've got to have, so you look puzzled, and that's good. These are very simple systems. So actually, I should have alluded to this already. When you look at the big systems, what have we done? We've tried to make them bigger and bigger and bigger for economies of scale, and we've tried to get higher and higher power density out of these systems. Again, to make them more economical. Well, what you do then is you've got higher pressure systems, you've got more complicated systems, you've got more safety systems. These microreactors, or at least most of the developers that are working on them, have gone in the complete opposite direction. They're very simple, low power low pressure or atmospheric pressure systems. Very, very simple. In fact, several of the designs have no moving components in the core. So that's how you get there, just through simplicity. Now, their energy density is nearly as good as what you would get out of a traditional like LW, for example. So there's trade-offs that get made. Here's some examples. I mean, you probably can't see a lot of, there's not a lot of detail here. A couple of the designs really were spurred by research at the Los Alamos National Laboratory around what they called megapowers. So you can trace the origin of Oklow's design and the origin of Westinghouse's Avinci design back to that was done at Los Alamos here. It's a schematic to give you some kind of scale and size. We can put 2 of these in this room. This is another company called HolosGen with this isn't real, with a depiction of their system deployed in a remote mining application, just to give you some perspective. So with all that background, our strategy around advanced reactors really all starts with microreactors. The other reason I like it as a laboratory is because it's a lot easier to license a non-light water reactor system if it's simple than trying to go license a big like molten salt reactor as your first kind of foray into advanced reactor licensing. Supply chain is not there for these big other reactors, so everything is smaller, supply chain is smaller. A high assay LEU issue in terms of supply. We have plenty to do several of these. We need some wins. That's another thing in the nuclear space. Things we can do. And then lastly, they're an incredible platform for innovation. So if I went into the NRC and I said, I want to talk to you about autonomous control of a NuScale reactor, that conversation would go nowhere. Talking about autonomous control of a microreactor with its simplicity, and they're actually engaging in that conversation and starting to think about what that would look like. I think we can learn a lot here that ultimately can be deployed to bigger reactors down the road. So we are working very hard to demonstrate at least 2 microreactors by 2025, and we're working with many more than 2 companies to do that. I do think one of them is likely to be the Department of Defense Strategic Capabilities Office, Mobile Power, that's a lot to say, Mobile Nuclear Power Project. Their schedule is 2024. And so looking for deployment after that. We're working very closely to support a utility called UAMPS and NuScale to build the NuScale reactors on our site by following their licensing progress that they're making. We're helping them not only with site and siting data and so on, but also through non-technical things like power purchase agreement. The intention is to use one of the modules to power our site. Because a lot of this is not technical, it's financial. We're working very hard. I hope many of you are already aware of our talks on the versatile test reactor to establish fast spectrum testing capabilities in this country. That's a project among multiple national labs, multiple private companies like GE, Hitachi, and Bechtel working to do that. I know you all don't speak DOE language, but they've got mission needs, CD0. They've got all the paperwork done for CD1, that's conceptual design and cost and schedule refinement and a number of things that go into that, and making very good progress. Many of you you guys probably don't read budget language like I do every day. Budget requested $295 million for this project next fiscal year. They may or may not get it, but that's the kind of money that we need to do that. And the whole strategy here is these things will all enable whatever comes next, whether that's molten salt reactors, high temperature gas reactors, whatever the world needs. So to do all this, we're talking multiple reactor demonstrations. The NECA legislation authorized something called the Center. That is the whole mission of that is to demonstrate reactors with an ion deployment. Just to be clear, we're not losing. We don't want to demonstrate reactors that are not commercially viable, because then that's the end, and that would have been a failure. So we want to make sure that we're demonstrating reactors that have commercial value on commercial deployment. Yeah.
So what's the price for your microreactors? What is it being priced at right now? And I know that will change, but.
So most of the companies, so we're not designing microreactors for commercial deployment. We're supporting others, private companies. Most of them, and most of them won't tell you. I mean, the flat answer is they won't tell you. But they'll tell you what they're competing with. NEI has a report, by the way, that estimates some of the price points. But most of them are trying to target, well, I mean, you want to go as low as you can, but they feel very relatively confident, I guess, they can compete with like the 50 cents a megawatt hour kind of price target. But this remains to be seen, so I'm always a little bit leery of talking to those numbers.
And we're going through the licensing process, right? As you mentioned before, what are some of the challenges? Because NRC is set up differently, right? They're used to the like already
Exactly.
Exactly. How are then they adjusting or reformatting for your micros, your small?
So, right. So that's a great question. And by the way, on NuScale, just so you know, the price target for them is $55 a metric a megawatt hour, which is the same as like 55 cents in the other terms. NRC, this is why I say I love the microreactors, because trying anything significant and complicated other than a light water regulations are written around, even all the exit scenarios and things are written around light water reactors. And so there's a number of companies like Oklo talking to them and basically not following, the traditional guidance documents. I wouldn't say throwing it all out and creating something new, but it's a round peg in a square hole. It doesn't fit. And so they're going through that process right now. That's also why I say I'd rather go through that process with a small, simple system than a big system. So, but that's going on right now. Yeah. That's actually right. Good. Thank you for that. So I didn't talk much about high-mass ALU. Let me just mention it really quickly. So most of these designs are trying to use approximately 28%. They're trying to go to the threshold of what is considered low enrichment. We don't have a enrichment capability to fill this need. We really don't have a supply chain for high-mass ALU. We actually don't have infrastructure to support high-mass ALU either. So this is a big challenge. Again, if we wanted to go to big reactors and had a lot of high-assay LEU need right away, we'd be in trouble from a supply chain perspective. We're still in trouble from a supply chain perspective, but we're working everything that we can, at least in the lab system, and beyond, to try to fill this need. So we've been processing old EBR2 fuel for years. That's actually high-enriched uranium fuel. And so we extract the uranium, we downblend it to less than 28% for waste. We're gonna dispose of it. And so we've retooled all that to clean it up more and get it uniform to provide high-assay LEU up to 10 metric tons to support initial small reactor demonstrations. We're working with another process to where we might be able to access the the HEU from other spent fuel forms, also extract the HEU, downblend it to high-assay LEU, and provide it for reactors. And then that's what I'd call a midterm strategy. And then finally, we've got to reestablish enrichment capability. The department contracted with a private company called Centrus, $115 million over 3 years to reestablish enrichment capability to fill this need. But there's a lot of work here. So this is probably the biggest supply chain issue, but there's others. So I mentioned it because it's kind of the biggest. So I'm going to switch gears here and talk about part of the reason I'm here. We're doing a lot, all right? We're trying to build a lot of reactors. I didn't even talk about much of the underlying research, the modeling and simulation that we need to do, the development that we need to do, the fuels development, the materials development, all of the things that I hope you all kind of work in areas that enable this. And so my biggest concern with these things that we're trying to do is we won't have enough talented people to execute. So this is a big concern for me. We've been growing tremendously. We've grown by over 100 people just in my organization in the last 2 years, and it's still not enough. So this is a real concern. You can have all the money in the world, but if we can't spend it and we can't spend it effectively, this opportunity will be missed. So I wanted to let you all know about internship programs at the laboratory. I guess you can't read all that. Bottom line is that's going on right now. So if you have applied already, great. If you're not sure if you're interested or not, come at the end and we can talk about that. If you've applied already and you haven't heard anything back, don't be shy. Our processes are like any big bureaucratic process. You apply, somebody looks at it all, and maybe it goes to the right staff member to make a decision, or maybe it doesn't, okay? I'm trying to get that better, right? But it is what it is, and we got some work to do. So if you're applying and you want to come to the laboratory, then I would say apply, but also shoot an email to do a quick Google search, who's the right person that might. If you don't know who the right person is, send me an email. Okay, I'm pretty easy to get. It's john.wagner@inl.gov. I will help do the matchmaking to make sure that somebody sees your application. My biggest fear is we got great people in the pool and the right people don't see that applicant, and then no contact is made. The other thing is, obviously I want you to come to INL, but there's a whole national laboratory complex. And I think I started my career as an internship at Oak Ridge National Laboratory. Scott, you were an intern at Oak Ridge National Laboratory at one point. Then we were both interns or graduate research assistants at Los Alamos National Laboratory. That was influential in my career on whether I went to a national laboratory or not. So it's a great opportunity to find out, hey, this is for me, or maybe it's not for you. And that way you learn that and you find out. There's a number of other opportunities. I've talked to some of the professors over the day about INL graduate fellowship programs. Honestly, when I was in school, I wish I had that kind of program. It pays pretty darn well. And you spend first couple years here, next couple years there. I don't think, we did put the money on there. So $60K a year, I guarantee you I didn't make half of that a year when I was a graduate student. So anyway, hopefully that would be enticing for me. If you have questions about that, happy to talk about that. And I don't know, Yusri, do you have materials on that if they have questions? Anyway, we can get more. I don't know if I've got contact.
Citizenship required for those?
No, it's not. No. And that's another thing, by the way, that it doesn't hurt if I get involved with a little matchmaking. So keep that in mind as well. Postdoctoral program, we have several distinguished postdoc opportunities. And then we have kind of your standard, not that these aren't good, but your standard ones, and then these are a little bit special with some additional benefits like access to LDRD money and things like that. So there's all kinds of opportunities. These are, I just took a snapshot of open positions right now, and you get some idea, everything from entry-level positions to a bunch of department manager positions. There's even, it won't show up here, but there's a chief scientist position, the position I started at INL with. Materials and Fuels Complex open. So if you know anybody interested in that position. So there's a lot of positions open, but also keep in mind that if you go to this place and you don't see a position that you're interested in, there's a whole lot of other positions that are currently trying to be filled, but they're open for a certain period of time and then they close and you don't see them anymore. But they're actually still ongoing. Resumes are being reviewed, interviews are happening. So again, I would encourage you, please don't go to our website if you want to work at the laboratory and go, I didn't see anything, so there's no jobs at INL for me. Send somebody an email and say, hey, I'm interested in an opportunity at the laboratory. Here's my CV. If you can help me with that, great. And I know I personally react to those all the time. And then there's contact information. Will they get these slides? Okay, all right, and just in case you want some more. I've just got I think one more slide, or this one, and but I'm kind of close to time. So I'm going to stop here and see if anybody has any questions before I talk anymore. Hi.
Can you give us like an overview of what it is working at INL?
What it is working at INL.
How would like a typical day look like?
I'm sorry?
What would a typical day look like?
It depends on who you are. So a typical day for me is meetings all dang day. But it depends. So there's one person's day might be, I could put it on the spot where he's probably in front of a computer screen most days, pretty much all day, meeting with peers and discussing, code interfaces and things like that. So a lot of folks do sit in front of their computer most of the day. Most of you as graduate students do that as well. Then there's opportunities for integration among different people. So those are more, I said meetings as if it's a bad thing. Sometimes it's very good in terms of collaboration. There's a variety of experimental facilities. If I walk over and I meet with Patrick Calderoni's instrumentation and sensors department team, they're in the lab most of the time. They're making thermocouples or testing thermocouples, or they're developing new sensors and testing them, putting them in a variety of kind of difficult environments. And so it varies from people who are probably more computer focused to people who are more experimental. There's a lot of hands-on jobs. I'm not sure that's what you all are interested in, but think about a hot cell technician, manipulator. Think about an instrument scientist. Doesn't sound fun to me, but sitting in front of a TEM all day or most of the day, or a fib. So I don't know, does that help?
Yeah.
Okay, all right. So it does vary. It varies kind of what you're interested in, but it really comes down to maybe office type work versus in the field experimental type work. Yeah.
Sorry, one more question.
No, take it.
Going back to your opening point where you mentioned the pessimistic and optimistic views of the industry, that's kind of where my question stems from, because you also talked about how media picks up a lot of negatives from our industry, such as closing down of reactors and such. But at the same time, this presentation was full of all the great things that we do and collaboration with universities that labs come up with, like ETR and so on. Not just these sensitive areas of nuclear, but there's other excellent things that go on in our industry, but those are never picked up by any media, except for nuclear related, like ANS News and such. Why is it that, in your opinion, any light you can shed on this, all this negative stuff goes into general media,
Yep.
but the positive stuff is never picked up?
Yep. So there's
Someone said to me one time that no news is good news.
I think that's how the nuclear industry, that's an attitude that's probably prevalent, and that's an attitude that probably worked in the 60s and 70s. It doesn't work anymore. People want to be inspired. People want to be excited, and they want to know, they want to be associated with something that's cool. And I'll tell you, I had discussions with NE for years, Office of Nuclear Energy, about raising their awareness, raising the awareness of the good things. And there hasn't always been so many good things, keep that in mind. But they said, it's not our job. We don't do that. It's kind of almost the no news is good news philosophy. That changed with Secretary Perry. So Secretary Perry, I know he got laughed at a bit when he said, we want to make nuclear cool again. But he hired a political, Susie Jourowski, and said, Susie, make nuclear cool again. And so I don't know if you're on Twitter, and I don't know if it's reaching you or not, but they've been doing a lot of things to raise the profile of nuclear, to get some of the positive news stories out. In my own organization, I had the same kind of reaction. It's like you think I'm a director of a research organization, so that's my focus, right? But I look at it and I go, we have to improve our communications. So I've gone and kind of revamped our communications people to get press releases out, to get things out so people can hear the good things that are going on. But we're still not doing it. I mean, there's still a lot of work to do in that space. But what I do see is things turning in the right direction. But then the other challenge here is, do you reach the nuclear, are we just reaching each other or are we reaching outside? We talk actively about the nuclear echo chamber. We all go to the nuclear meetings. We go rah nuclear, but that's not going out to the broader public. Now, in Susie's effort is trying to do that. A&S is doing more of that, but there's a lot more to do. You'll see, I think next week maybe, they'll demo A&S and National Geographic a virtual field trip to INL with a couple of young people, and they're kind of, they're fun, they're exciting, and they're going around and trying to make nuclear cool and conveying that. So there's a lot. Sorry to give you a long answer, but we haven't done a good job. I think we're starting to do better, but all of you, one more kind of comment. 5, 6, 10 years ago, I get on a plane and people say, you sit down next to somebody and say, what do you do? I usually would say engineer. Because if I say nuclear engineer, then somebody will go, oh, damn nuclear engineer. So, and I realize that's dumb. I should totally tell them I'm a nuclear engineer, and then I should tell them why that's so cool. And now, it doesn't mean they're going to think it's cool, but I get in these conversations, and more times than not, at the end of the flight or whenever, they go, wow, I always thought it was like scary, and it was weapons, and it would blow up and so forth. And I'm not going to say they're convinced, but at least they have information, and they have a different perspective. And so each one of you could become a communicator for nuclear, if you choose to be. Even family events and so forth. Are you talking about it, or are you avoiding the conversations? Think about that. Yeah.
Do you have any comments on the White House budget for the next fiscal year that is going to determine the shift of focus to cybersecurity and artificial intelligence?
So I don't have a lot of comments on the president's budget. I will admit to you I focus mainly on the nuclear energy piece of it. I am aware that they're planning to put a lot more money in cyber and artificial intelligence. I think that will happen. And so my comment would be you're going to see increasing budgets in those spaces. It's almost like we can't throw enough money at cyber or artificial intelligence right now, which is an opportunity for all of us to potentially, benefit from that. It's a budget request. I mean, we've seen year after year that the ultimate budget and the budget request often aren't aligned very closely. But on the NE side, I'm going to focus my remarks more on the NE side. The budget request last year was like $800 million. You can tell I don't pay that much attention to it. It's $1.2 billion. So the trend is very different. And the trend is driven, the language will tell you, it's related to the importance of being a global player in nuclear energy. And so that's a data point I do pay attention to. And then the versatile test reactor, $295 million, that's pretty hard not to get your attention with that kind of thing. But ultimately, let's see what the House and Senate do. That'll be what really what we execute. So. Anything else? I'm happy if you want to stick around and talk about these two topics. Who should I decide?
Can you do it in 1 minute?
No. So I will do it quickly, and I'll stay around as long as anybody might want to talk, but I also want to respect your time. I talked a bit about our strategy overall and our priorities and so forth, but you also heard me talk about how evolutionary a lot of the nuclear energy research is, how risk-averse the utilities are, how risk-averse a lot of nuclear organizations are, and it really holds things back. We incrementally improve things. And so we got my team together and said, what would really move the needle in nuclear? And there's a lot of ideas, and I'm not even going to say these are the two best. Well, no, I'm going to say I like these two the best out of what came out. And so we decided to come up with major initiatives that we thought would really move the needle in nuclear. We came up with these two. This is nuclear materials discovery and qualification. Fundamentally, we've reduced the time it takes to develop and qualify new nuclear fuels and materials, but not by a lot. Okay, we still have the same approach, and a number of those pieces of the approach are very long. Okay, making a material doesn't take too long. Pre-irradiation characterization doesn't take too long. Irradiation, getting neutrons, getting displacements per atom on a material that's relevant, that can take quite a long time. Then what we would do is we would pull it out of the reactor. It sits, it cools. Then you would do some coarse grain post-irradiation examination, some segmentation, and you would do some microscopy on it. You would characterize all the features you want, and then generally, this is the real kicker, then generally you would look at that and go, it wasn't quite what I wanted. All right, so and at that point, you're 10, potentially 15 years down the road. Let's just say 10, because you could argue it's not 15, and then so you go all the way back and you start over again. So what we focused a lot of time on over the last 20 years as a community is shrinking those pieces, trying to get more DPA faster, trying to reduce the time from when we pull it out of the reactor to small sample PIE and microscopy to get the dose rates down so you can do it sooner and faster. And then our level of instruments is incredible, by the way. I'm not an instrument scientist, but that's amazing. And that's a big advancement. So we've tried to take this thing and squish it, okay? And that's good, that's great. Kudos to everybody involved with that. But if you look at other fields, they do it differently. They do, and I got my kind of eyes opened by pharmaceuticals and biotechs, where they don't do a few samples at a time. They do thousands of samples at a time. They push as much through their process as fast as they can. They use things like modeling and simulation to decide out of, say, 1,000 by 1,000 test matrix, which ones they can do and infer the behaviors between, for example, and go through it. And so the whole field, material scientists, by the way, maybe that's what makes me dangerous, about high throughput experimentation and combinatorial material sciences. And so what we got together is that we should be applying this to nuclear fuels and materials discovery and qualification. As we started talking to the community, not me, guys who are a lot smarter than me, there's a lot of work going on in other fields in this area that we can leverage. And so this has really become an exciting topic that's actually not just like but leveraging a variety of material genome types of activities and activities across the entire kind of spectrum of universities, companies, labs, Office of Science, and so forth. And there's a lot to this. This is not an easy thing. This is going to be a long-term big thing to fundamentally change. But my dream would be you pick a certain class and you start with a giant test matrix of possibilities. You run it through that. Let's say it's a 10-year process, or hopefully it's less than that. And at the end, you've got a rich data set that you've got materials for whatever you wanted, but you've also got a material library for other things that you didn't actually want right now. And so that would be a very different thing. Quickly on the fission battery initiative, it's about microreactors, you already get that. But microreactors are going to either be very niche market or they're going to be everywhere, okay? And that will depend on cost and their deployment kind of paradigm, all right? So if we could get to a point, so we're starting with the end in mind, if we could get to a point where you can literally order a reactor like a diesel generator, hook it up, push the button, and it just provides power as you need it, not even full on 100%, but as you need it, drain it like a battery, but we're talking 10, 20-year time frames, not 24 hours or 4 hours, and not have a security presence, potentially, not have any operators near it. It's just a cargo container sitting out there that's powering everything. If we could get to that point, that's the market opens up like crazy. Then you say, okay, that's a nice dream, John, really. But what would you have to do? Okay, what's the research look like to enable that? Because the micro-reactor developers, they want to get there, but they're focused on demonstrating as quick as possible, so not really focused on longer-term R&D at this point in time anyway. So you've got to have autonomous control. You've got to have defendable autonomous control. You've got to have instrumentation and sensors that support that. You've got to have physical security mechanisms. You've got to have a variety of transmitters and tamper detection. That's not even hard. That's not even really difficult stuff. You've got to have a regulator that's willing to talk to you about this, which actually I would argue our regulator is willing to talk to you about that. You've got to, and then ultimately to be really economical, you want it to really work in an operational environment where you drain it as needed. So the sun comes up, you start draining less off of it. Sun goes down, you drain full up as much as you want. And instead of like load following on existing plants where you're still going to defuel about every 18 months, this is a 10-year, and if you use it at only 50% capacity, well, now it's a 20-year lifetime. All right, you're still getting the same juice out of the thing. And so there's materials issues, there's expansions, there's thermal behaviors that you need to be concerned about. There's heat pipe research, at least in some of the concepts, that would need to be done to enable that. So there's a whole research portfolio that would enable this. I'll call it a dream, that you have a system like this. But none of it, in my mind, is not possible. The regulatory and safety security things are probably the most difficult because they involve public perception and acceptance and things like that. And those are really like less technical. They're more kind of political and social. So anyway, so we're laying out the research portfolio to enable this, or that would enable this. We've been talking to Yusri and others about involvement from NC State on both of these. So if you're interested in either one of these, obviously I could provide more information, but we're looking to engage. I would like, in my personal mind, I'd like to get the entire nuclear community engaged around these two things to help me, because I can't do it all. We can't do it all. We need a lot of folks playing different roles. And by the way, on this one, I need cybersecurity folks. You're asking about cybersecurity. I'd like to leverage all the money that's being spent in cybersecurity to help me with that, and AI as well, potentially. So, okay, so that was way more than 1 minute. Sorry about that. Okay. Thank you. And I'm going to stick around in case anybody has any questions or wants to talk for a little bit, right?
Yeah.
Okay.